Okay, so welcome back everyone. So in this video, we'll be looking at the notion of regular languages. So what is a regular language? Well, we have the definition here. So a language L is regular if there exists a DFA M such that the language accepted by M or the language recognized by M is L. So in other words, right? In other words, L is regular if and only if there exists a machine M, which is a DFA that accepts L. Okay? And so these languages, they're known as regular because they have this sort of intrinsic property within themselves. So you can think of the family of regular languages, right? So you have a family of regular languages, which is just the set of all languages, right? L, let's say 100, whatever. All these languages, what they have in common is that they have some machine, right? Obviously, it's not going to be the same machine, but each of them have some machine that's a DFA that accepts it. So really what we're saying is that the language isn't too complicated to recognize, right? Because a DFA, as a machine isn't that complicated, right? It has a finite amount of memory and everything it does is deterministic, right? So really what we're doing here is we're sort of classifying all these languages as being relatively simple or relatively regular, okay? And that's this kind of mapping that you should put in your head, is that these languages are regular because they have some property within them that allows them to be accepted by a DFA, right? They're simple enough that a DFA can be created to accept them. And so one way to show that a language L is regular is to show that there exists a DFA M that accepts it, right? So that's very intuitive, right? Based on the definition. And so that's exactly what we're going to show in this example. We're going to try to show that the language L, where L is the strings AN, where N is a multiple of 2, but not of 3, is regular. Okay, so first of all, what are the strings that actually belong to this language? Right, well, N has to be a multiple of 2, but not 3. So, let's say A0. Well, 0 is a multiple of 2 and 3, so that's no good. A1 is a multiple of, 1 is a multiple of neither, right? 2 is a multiple of 2, but not of 3, so that's good. 3 is a multiple of 3, but not of 2, so that's no good. 4 is a multiple of 2, but not of 3, so that's good. 5 is a multiple of neither because it's prime, so that's not good. 6, well, 6 is special, right? Because 6 is a multiple of 2 and of 3. And so that doesn't respect this definition, right? Because N has to be a multiple of 2, but not of 3. And so that I would reject, right? That I don't want to accept in my machine. Now what else? So A7, that's not going to be in my language because it's prime. A8, yes, this is a multiple of 2 and not of 3. So that's good. A9, that's a multiple of 3, so already that's not good. A10, this is a multiple of 2 and not of 3, right? And so on. Okay, so what I wanted to do from this short exercise is I want to show that there's actually a pattern here of what's going to be accepted and what's not going to be accepted. So all of the integers that are multiples of 2 but not of 3 are actually going to be on this kind of on this sequence of integers. So it's going to be 2, 4, 8, 10. You're going to skip 12, but you're going to catch 14, catch 16, you're going to skip 18. So really what you're doing is within these 6 elements, right? So within modulo 6, okay, how do I get modulo 6? Well, here I got modulo 6 because I'm multiplying 2 prime numbers, 2 and 3, getting a cycle of 6, right? So this doesn't always occur if what I'm working with aren't prime numbers, but in this case I'm lucky. I have 2, which is prime, and 3, which is prime. And so the cycle that I need to look at to find integers that are multiples of something and not of that other thing, that cycle is only going to be within these 6 elements, right? So it's just going to be a reoccurring pattern, right? It's going to be, say, n, so I'll have 0, 1, 2, 3, 4, 5, then 6, 7, 8, 9, 10, 11, then 12, 13, 14, 15, 16, 17. So this is never going to be accepted, right? Because this is a multiple of 2 and 3. This is not going to be accepted because it's neither a multiple of 2 or 3. This is always going to be accepted. This is going to be rejected because it's a multiple of 3. This is going to be accepted because it's a multiple of 2 and not 3. And this is going to be rejected because it's not a multiple of 2. Okay? And so really it looks like what I'm looking for is 2 mod 6 and 4 mod 6. Okay? Well, how do I actually now represent this in a machine, right? Well, it's actually quite simple, right? So let's say I'm at Q0. All I need to do is create a cycle of 6 edges, right? So I create a cycle of 6 edges. 3, that's 4, that's 5, that's 6. And I read A's, right? So imagine I have, on my input string, I have AA, right? So I have 2 A's. Then I start at Q0, I read an A, I go to Q1. I'm at Q1, I read an A, I go to Q2. And so I should accept this, right? Because 2 is a multiple of 2 and not 3. So this should be an accept. And then from Q2, let's say I actually have 3 A's. So now I go back to Q3 and I'm back to rejecting because Q3 is not going to be a final state. But if I go to Q4 by reading another A, now I should start accepting again, right? And so this guy is going to be my 2 mod 6, and this guy is going to be my 4 mod 6. And in fact, each of these other states are going to play a certain role, right? Q0 is going to play the role of 0 mod 6. Q1 is going to play the role of 1 mod 6. 3 is going to play the role of 3 mod 6. And 5 is going to play the role of 5 mod 6. And so we see that within modulo 6, the only integers that are going to be accepted are going to be the ones that, once you divide by 6, are going to have remainder 2 or 4. And those are exactly the states that I've made final states. Right? So I have my machine M that is going to accept the language L. And so this shows, right? So this shows that L is regular. So in other words, L has this intrinsic simplicity to it that I can create a machine, a deterministic finite machine that accepts it. Okay? And so that's how you would prove that a language is regular. Excellent. So this concludes the video series, the tutorial video series on deterministic finite automata. We're going to be discussing a lot more interesting things in future videos. One of them is going to be tackling the idea of non-determinism. So when your control unit or your machine has more than one option, what happens at that point? So be sure to stick around for that. And so I will see you in the next video.